Meine sehr verehrten Damen und Herren, bitte begrüßen Sie mit mir den Technical and Marketing Director Europe, Herrn Rahman Jamal.
Ich begrüße Sie ganz herzlich auf der VIP 2011. Ich hoffe, Sie haben gestern einen schönen Networking-Abend gehabt. Apropos Networking, VIP ist so eine Art Networking-Community für Ingenieure, für Wissenschaftler, aber auch für die Fachpresse. Hier haben Sie die Möglichkeit, Anregungen zu sammeln, über Applikationen zu reden, Erfahrungen auszutauschen, aber auch Lösungen miteinander zu besprechen. Und gerade die Lösungen, Ihre Lösungen, leisten einen entscheidenden Beitrag, den Alltag zu verbessern, die Gesellschaft zu unterstützen, aber auch die größeren Probleme der Menschheit zu begegnen. Jede Lösung, die hier präsentiert wird, ist in ihrer Art einzigartig, aber dennoch verbindet sie etwas Entscheidendes, was sozusagen nicht sichtbar wird, dennoch immer vorhanden ist. Diese Grundlage, auf der all diese Applikationen, die Sie realisieren, basieren, nennen wir Graphical System Design. Nun, bevor ich in die Details des Graphical System Designs eintauche, möchte ich kurz auf Englisch umschalten und eine Kollegin aus USA vorstellen und auch auf die Bühne bitten. So, before I dive into the details of Graphical System Design, I would like to welcome a colleague of mine from Austin, Texas, Norma Dorst. But first, let me introduce Norma to you briefly. So Norma has been 15 years with National Instruments working in the product management area, and she was instrumental in releasing products such as LabVIEW Real-Time, LabVIEW FPGA, but also the Express technology in LabVIEW. Currently, she is in the corporate marketing department and evangelizes our vision and our mission. So with that, please help me welcome Norma Dorst to the stage. Norma.
Hi. Thank you, Rahman, for the privilege of addressing VIP Days this year. I am so happy to be back in Munich.
Wonderful to have you here, Norma. I just mentioned graphical system design as the keyword. Now, it does not really sound very new. It sounds very familiar, so...
It is familiar. I think if you ask our founders, they would say that they envisioned graphical system design from the very beginning. In fact, Dr. Trouchard, our CEO and co-founder, has a slide he likes to show when they were first trying to name LabVIEW, and we nearly called it the Graphical Measurement System, or GMS. So I think to understand graphical system design, you really have to go back to our beginning, our mission and our purpose. We believe that engineers and scientists are the ones creating the systems that help impact humanity, whether it's managing resources like clean energy and water, or developing devices that help save lives in medicine. And so our mission as a company is to equip engineers and scientists with the tools that accelerate productivity, discovery, and innovation. Our tools should never be the limiting factor to achieving these goals.
So let's take an example. If someone is coming from the design area and he's using mathematics as his first-class citizen tool, and then he's trying to solve also a measurement task at the same time, it's a very difficult task to bring these two worlds together. So how can we help them?
You're right. And actually, tools sometimes get in the way of them being able to do that. So instead of domain experts being able to focus on solving the problem and use their expertise in energy or communications or machine building, they spend all their time learning the mechanics of the tools themselves. This is not a situation that we have to accept. As engineers, we need tools that are as productive to doing our job as the spreadsheet is for financial analysts. And this is the driving need behind graphical system design, this software-centered, platform-based approach to accelerating the development of any system that needs measurement and control.
So in other words, if you were able to transfer your problem from a hardware-centric to a software-centric perspective, you could solve your problem as it arises. So let's take an example, smartphone, which just happens to be a phone. There are many functions inside a smartphone, and depending on the app, depending on the software that you choose, you can kind of convert the personality of the hardware into the device you need. So is that the approach that you're referring to?
Rahman, a smartphone is a great example of where a software-centered approach helps you adapt to changing technology over time more easily. If you think about a phone just 10 years ago, its purpose was to transmit and receive signals clearly and reliably. That was what it did. But now, as it's evolved into a mobile computing device, the functions it does escalated in complexity. And so in order for you to create, build, and test these phones, your systems have to escalate in complexity as well. And this is where using software and modular hardware can help you adapt and harness new technology over time.
So the complexity is increasing in general. It's not only the smartphone, but also all the products coming out today are very complex. So you'd like to use commercial off-the-shelf technology. You'd like to easily configure your whole system and so on. So, you know, that's a very challenging task, isn't it?
Yes, it is. But, you know, here's where, as a graphical system designer, you can have a very rich engineering career, building your career off of this platform. Because with graphical system design, you don't just concentrate or focus on one element of a system or have something that focuses on just a point solution. You have an entire platform that is both software and hardware. It is reconfigurable and modular. It allows you to abstract complexity in a significant way. It allows you to integrate commercial technologies very easily. And it gives you a single hardware reconfigurable architecture that can span across multiple target platforms. So let's take, for example, building an embedded system, because this is where graphical system design is really well illustrated in terms of how it can accelerate your development. In a traditional way of developing embedded systems, you're going to need expertise in analog design, in digital hardware design. You need C programming experience, VHDL experience. In fact, it soon looks like you need a whole team of engineers in order to develop quickly an embedded system. Is this what you want to do as an engineer, you know, to learn all of the mechanics of all of these tools, as well as, you know, try to figure out project management of an embedded system? No, I mean, the purpose of becoming an engineer was to create, invent, build. And so what you get with an integrated system platform, such as graphical system design, you can use that to push and boost your productivity in developing any system that needs measurement and control. In fact, if you invest in a platform-based approach, what you get is a basis from which you can derive infinite systems with a single learning curve. And this is what is accelerating the development of any system that needs measurement and control.
Okay, you said a lot of things, so let me
Yes, I
summarize. We are a bit skeptical
I
here
get
in Germany.
excited, sorry.
Yeah, we are a bit skeptical. So you said infinite systems, and then you said one framework for hardware and software, one framework where you can seamlessly integrate commercial off-the-shelf technology, and then also reconfigure it. I think that sounds too theoretical, too conceptual.
Okay, I know it's hard to believe, which is why we're going to spend the rest of this morning demonstrating how it works. So the fundamental concept is really this. Every system that needs measurement and control has essential elements that you need to put together. First, you need the I/O in order to interface with physical, real-world elements. Next, you need math, modeling, signal processing, some sort of way to get information from the data that you have. You also need to be able to interact with your system, whether it's through an operator interface or transmitting and receiving information or saving data to files.
Okay, that sounds very familiar. I think everybody knows acquire, analyze, present. So I agree with you completely.
Exactly. Okay, yes, acquire, analyze, present. Now we just need to add a few more elements to help people design, prototype, and deploy your systems. For one thing, you need something to run the system on. So whether it's a PC or a more embedded application, perhaps a single board with some processing elements to it and architecture for integrating peripherals, graphical system design provides you a single architecture to be able to deploy easily across those. And then secondly, you also need to be able to integrate any commercial technologies that may not be available in the base platform. So again, it needs to be an open platform for you to be able to easily pull in those pieces. And then you need a way to describe your system, right? And so it might be system timing, you know, what happens when in your system, as well as the functionality of the system components themselves. And some components are really well described because they run in parallel operation, for example, by data flow. But other system components might be better described using formulas or event or state-based solutions. The beauty of graphical system design is that it is an environment which houses multiple models of computation so that you can use the best tool for the job at hand.
So, okay, the first three building blocks, acquire, analyze, present, straightforward. I agree. Then you have the commercial off-the-shelf technology, it's also straightforward target platform. But the computational model of computation, very abstract term, and I think in layman's language, I would understand our user decides what language he knows. That's what he's going to best use to describe his problem. So basically, models of computation is his language of choice to decide what he needs to realize. So is that what is it about?
That's a great way to put it. In fact, the point of graphical system design really is to be able to efficiently and rapidly integrate all of these elements so that you can create systems faster.
Wonderful. So now I see the 6 blocks, and then I see a while loop and a clock. So that looks like a LabVIEW program.
It does. Does it look like LabVIEW? Yes. Yes, it does. Absolutely.
Okay. So I think that part is straightforward as well. Software, you know, we know LabVIEW. But how does all the hardware fit inside this conceptual framework?
Okay, well, let's get started with the proof then. So I will see you later, Rahman, and happy hunting with your angry eagles.
Okay.